All right, you guys, in 5.3, we're moving on into really the later part of this chapter here, and we're getting to the big concept that we do in almost every chapter here in Algebra 2, learning how to solve equations of a different type than maybe that we've solved before. So here in 5.3, we're really learning how to solve certain, not all, but certain third degree, fourth degree, fifth degree, maybe even polynomial equations, and we're going to do that here, guys, by the method here of what we would call simple factoring. It's going to get a little bit different later on in this chapter. But for now, we're going to learn a couple of new factoring methods starting right over here. And the first of those new factoring methods that we're going to begin right below it here is called factoring by grouping. And to my knowledge, this is something pretty new for you guys I don't think you've seen before. Please take a note of this little comment right over here. Grouping only works when we're dealing with an even number of terms. Now, you wouldn't do it for 2 terms, but 4, 6, 8, these would be problems that you can do grouping on, and I'll tell you right now, we hardly ever do 6 or 8. So it's pretty much used for 4-term polynomials right here, pretty much exclusively. So let's take a look at this example right here. We've got 3x cubed minus 12x squared plus 7x minus 28. As far as I'm aware, you guys have never been asked to factor something like this before. This would be a 4-term cubic polynomial. And the way we're going to do this, guys, as the name suggests, is we are going to group 2 out of the 4 terms together. And almost always, we simply are able to group them in order. So what I'm going to do is throw a set of parentheses right here around the first 2 terms in that polynomial. And then, this won't always work, but it does in this case. I chose this problem specifically so that it would. I'm going to group the 3rd and the 4th term together. And what I want you guys to notice is that I had to be very careful about the numbers that I chose for this problem. You can't just be random with it. But if you notice your coefficient right here on the x cubed term is 3, and right next to that, we have a negative 12. 3 to negative 12. And then look at the coefficients over here in the second set of parentheses, a 7 and a negative 28. Now, you don't really need to write this down, but maybe you'll notice here that negative 12 is this 3 value here multiplied by negative 4. And then over here, to get from 7 to negative 28, well, that's the same relationship. You multiply by negative 4. And when you have that same relationship there, that means that factoring by grouping is going to work. Let me show you how. The first thing we're going to try to do now is pull out a greatest common factor from those 2 terms right there. And from 3x cubed and 12x squared, we can bring out a 3, and then they both have 2 x's. So we'll bring that 3x squared out in front with basically the reverse distributive property, and now we'll write what's left. Well, we pulled out a 3x squared. That leaves us with just an x from the first term and then a minus 4 from the second term. Okay, so that's just a little bit of simple grade GCF factoring. And now this plus sign that was in the middle right here comes straight down. We don't lose that. And now we try to pull out the greatest common factor from these 2 terms. And this one's a little simpler. That's just a 7 that we can bring out in front. But now what's left? When we divide out the 7, we get an x minus, and 28 divided by 7 is 4. And it's not a coincidence right here, guys, that this factor right here of x plus 4 and this factor of x minus 4 are identical to each other. So now what we want to do is treat this expression as one large binomial. Okay, the 2 things that I've underlined right there, we have our first term on the left plus our second term on the right. And now we're going to notice here that these 2 big terms underlined in blue have a common factor. They both have an x minus 4. And so what do we do with a common factor? We bring it all the way out in front, and we're basically doing GCF factoring again. So I pull out the x minus 4, and that comes all the way out in front of the expression, and now I start a new set of parentheses, and I say, all right, what's left over from each term after we've taken out the x minus 4? Well, here initially we're left with a 3x squared, and then that plus sign again comes straight down here, and what are we left with here after we've pulled out the x minus 4? Just a 7. And that right there, you guys, is our fully factored expression right here, and that's how you factor, in this case, a 4-term cubic polynomial by grouping. Now, I would imagine a lot of you would probably want to skip this part, but I'm going to run through it anyway. You can check your answer to any factoring problem, you guys, just by making sure that if you were to multiply out your final answer, you get right back to where we started. So you certainly don't have to do this, you guys, but I would really recommend that you do it once in a while just to see if you're right. Our answer is written as the product of two binomials in factored form, so I'm going to do FOIL. First product would be x times 3x squared, so that would get us a 3x cubed. Then I'm going to do my inner product next. 4 times 3x squared is a plus 12x squared. My outer product here and here, x times 7 is a plus 7x. And then, I just realized a mistake that I made here, guys. Sorry about that. That should have been an x minus 4 that I pulled out in front. I'm looking at this minus right here and this minus right here, so my goof up was on that term right there. I was wondering why this wasn't about to work out right, so let's fix that. So that should have been an x minus 4 in the answer. Sorry about that, guys. And what does that do to my check here that I'm doing in green? The first term is still 3x cubed. That's right. The inner term now should be a minus 12x squared. There we go. Minus 12x squared. Outer product is still a plus 7x. And then the last product, here times here, negative 4 times 7 should be a minus 28. And if you look, guys, that is identical to the expression that was up here in black before I started messing it all up. So I feel pretty good about this answer right here, and we know that we got this one right. But again, just to be clear, the check is not your final answer. Your final answer is this factored form right here of the original. Okay, that is what factoring by grouping looks like. So let's kind of zoom out right here. I want to do one more example of that with you guys. There's a little quirk to factoring by grouping problems that happens once in a while, including on an example like this one. So 6x cubed plus 9x squared minus 8x minus 12, and here we go. Now again, I notice 4 terms within my polynomial right here. That's when I very often do factoring by grouping. And if you get in the habit of doing this, look at the ratio here of your first to your second coefficient. A 6 to 9 ratio simplifies to a ratio of 2 to 3. The same thing happens here on 8 to 12 if you divide both of those by a 4. So I feel pretty good about this one working out, but something interesting happens as soon as I try to do grouping. And I want you to pay attention to the signs of all 4 of the terms here. Positive, positive, negative, negative. All right, so if I were to do parentheses right here, as I normally do, everything is fine. That 6x cubed is still positive, and the 9x cubed is still positive as well. The weird thing happens when I try to do parentheses right here, and something there happened that I did not intend. Now remember, guys, in putting the parentheses there, there's a minus in between here that really needs to get distributed inside there. So the opposite of 8x makes that term negative 8x. That's what it was at the beginning of the problem, so that's perfectly fine. The issue happens right here. Now, I have to distribute this negative, and minus a negative 12 actually makes this term positive. And in the original expression, let's go back to before I started messing things up, in the original expression, that 12 was negative. So the problem with this one, what makes it harder than what we did in number 1, is that in number 1, this middle term was positive, and I didn't have to worry about this problem I'm having now. But in problem number 2, we have a little issue. Here's how we fix that, guys. Anytime there's a minus in the middle of this entire expression, you've got to do one little thing. You can go ahead and put parentheses, as it were, around the first 2. Then go ahead and put parentheses around the last 2, but we need to make sure that that 12 is actually negative. So to do that, guys, we now change this minus in the middle to a plus. And that seems like I'm just randomly changing here the 12 from a negative to a positive, but that is not what's going on right here. I'm actually trying to keep this thing the way it was. It was a negative 12, and now by distributing that negative to a positive 12, yeah, it does end up being negative. Okay, so let's look for a GCF now, guys. From 6x cubed and a 9x squared, we can pull out a 3x squared. And that will leave us with 6 divided by 3 is 2. X cubed, we pulled out 2 x's, leaves us with an x right there. And then a plus. 9 divided by 3 is 3. There were 2 x's. We pulled them both out. That's it. So that's just a little bit of monomial factoring now from the first binomial that we grouped together. And now here we go. This negative comes straight down right here. And what can we take out from an 8x plus 12? We can bring out a 4, no x's though. And in parentheses, 8 divided by 4 is 2, and there's an x right there. And because we made that 12 positive and pulled out a 4, that's now a plus 3. So we have two large terms, one here and one here, and what do they both have in common? They both have a factor, a common factor of 2x plus 3. So we're going to pull that all the way out in front. So the 2x plus 3 now gets yanked out in front, and what's left from each term? Well, from here, we have a 3x squared that remains, and from here we have a minus 4. Okay, it doesn't look like there's anything else we can do, so that, I believe, is going to be our final factored answer here. And again, you don't need to do this, but just to make sure that it's right, let's go ahead and FOIL out these two binomials and make sure we get right back to where we started in black. First product is a 2x times a 3x squared, so that would be a 6x cubed. My inner product, just because I like the order to be right, plus 3 times plus 3x squared is a plus 9x squared. So far, so good. Outer product, 2x times a negative 4 is going to be a minus 8x. And our last product right here, positive 3 times negative 4, is going to be a negative 12. And if you recall, that's exactly what this problem looked like before we did the grouping and before I changed the sign of the 12 inside the parentheses. So yep, that one works out as well. So that's two examples, guys, of factoring by grouping. And I wouldn't think that after just two, you necessarily feel like you have it completely down, but that's why you guys need to do a whole lot of practicing on your homework right here. Factoring by grouping takes a little bit of practice to get used to, but it's not all that bad. The next second method that we're going to talk about in this section right here is also something new. We're talking about factoring either a sum or a difference of cubes. Now, if that sounds just a little bit familiar, guys, there might be a reason for that. I'm going to write this at the bottom right here. This is one you guys already know, so we're not including it in our notes right here, but you did learn back in chapter 4 how to factor a difference of squares. And a difference of squares would be written of the form a squared, because we're talking squares, and difference means subtracting. So a squared minus b squared, and that one factors into the product of two conjugate binomials, a plus b times a minus b. So if you're forgetting or struggling a little bit with what that actually looks like, you might have seen a problem like, x squared minus 25, for example. And you would notice, I hope, that it's a binomial expression, only two terms, and that both the first term, x squared, and the second term, 25, are perfect squares, and they're being subtracted. And we factor that one into a is the square root of the first term, the square root of x squared is x, and then a plus. B is the square root of this term right here, the square root of 25 is 5, and then its conjugate binomial, which would just be x minus 5. And if you were to FOIL that expression back out, you'd get right back to where you started. X times x is x squared. The outer product is negative 5x. The inner product is positive 5x. They cancel each other out. And then the last product is 5 times negative 5. So you end up with negative 25. And check, that's right where we started. So this is something that you guys learned back in chapter 4. Now we're taking things up a little bit. And the first one we're going to talk about here is a formula for factoring a sum of cubes. So instead of squares, we're talking cubes now. That's why this is a cubed and this is b cubed. And obviously the word sum tells us that we're now adding these two numbers together. So we're going to have to get good at recognizing some perfect cubes. And some of you guys were still struggling with perfect squares, so I think we're going to make a little list of perfect cubes here in just a second. But here's the factoring pattern for a sum of cubes. A cubed plus b cubed breaks down into the following. It's the binomial a plus b, a being the cube root of your first term, and b being the cube root of your second term. And then that binomial gets multiplied by this trinomial right here, a squared minus the product of a times b, and then a plus b squared at the end of all that. That is the formula, you guys, for a sum of cubes. But then there's another one right here, and this is the formula for a difference of cubes. So now we have a perfect cube and another perfect cube, except these ones are being subtracted this time, hence difference of cubes. And you'll notice, guys, this is almost the same formula, except two signs get flipped around. The plus that we had right here in our first binomial now becomes a minus. So this one begins with a minus b. And then that gets multiplied by a trinomial of a squared, and instead of a minus ab, this one is now a plus ab, but we still end with a plus b squared at the end of all that. Now, guys, I hate to tell you, this is something you guys are going to have to study and memorize here. The factoring pattern for a sum or a difference of cubes isn't necessarily intuitive, and I don't think you're going to be able to just figure it out on the fly. So this is one you guys are going to have to work on. I do want to make one happy little note over here on the right. And let me pull a different color right here, guys. Let me go with that pen, and we'll do that. Okay. These two trinomials right here, a squared minus ab plus b squared, and then this trinomial right here, a squared plus ab plus b squared, these two trinomials, this is good news, guys, will never factor. If they did factor, we would have written it in factored form here in these expressions right here. So when you do start working here on factoring a sum or a difference of cubes, when you get this ugly trinomial here for a sum of cubes or this ugly trinomial here for the difference of cubes, you don't have to worry about factoring those any further. Those two expressions right there are never going to factor. So let's keep that in mind as we're moving forward. Okay, so let's see two examples, guys. One of each of these to kind of illustrate the point that we're trying to make right here. So our first one right here, guys, is x cubed and a minus 343. Now, wait a minute. Before I get into that, I said we were going to make a quick little list right here. So probably a good idea if you guys can just cram this somewhere in your notes, maybe up at the very top of your page. You guys hopefully by now are pretty familiar with the list of perfect squares. Numbers like 4, 9, 16, 25, 36, and so on. But you're probably less familiar with a list of perfect cubes. So we're going to run through this one. And I tell you what, just so you guys understand what's happening, I'll go ahead and put the left side here. The first perfect cube would come from taking 0 to the third power, everybody. And 0 times 0 times 0 is, of course, going to be 0. 1 cubed, 1 times 1 times 1 is just 1. So those numbers are true, but don't really help us that much. But here we go now. 2 cubed, everybody. 2 times 2 times 2 is going to be 8. 3 to the third power is 27, and we could keep going forever here. I'm not going to give you that many, maybe 10 or so. 4 cubed is going to be 64. After that, 5 cubed is 125, and I'm just going to work over here on the right now. 6 cubed, 6 times 6 times 6 is 216. 7 cubed is going to be 343. 8 cubed, 2 cubed, that's 2 to the 9th power. That is going to be 512 right there for 8 to the third. Maybe I should have written that out. 6 cubed. This one was 7 cubed. This one was 8 cubed. All right, we're going to do 2 more here, guys. 9 cubed is, if I'm not mistaken, 729. And 10 cubed, I'm kind of hoping you could do that one in your head. 10 times 10 is 100 times another 10. Just stick one more 0 after that 100, and you end up with 1,000. So this is a list of perfect cubes, guys, and really it's just these numbers here in the second column that are your perfect cubes, but I wanted to keep all that junk to the left of those just so you understood where those come from. And to be clear, these are not all of the perfect cubes, you guys. There's actually an infinite number of them. You know, you could take 538 to the third power, and whatever you get is a perfect cube, but this is probably the list of, 10 of them that you need to know. And to be clear, this one pretty much never shows up. We never really have to worry about 0, and 1 only shows up every so often. So, armed with that, let's take a look at what's going on here in this first example. We've got x cubed minus 343, and we're supposed to factor that. So, what we would need to do is think to ourselves, all right, this is a binomial expression. What can I do to factor it? And what I would hope you would notice pretty quickly is that x cubed, your first term, is a perfect cube. That one's fairly obvious. 343, well, if I go back to my list of perfect cubes, yep, 343 is the cube of 7. So that tells me that what we're dealing with right here, you guys, is a difference of cubes. Difference because these two numbers are being subtracted. So what are we going to do with that? It might be a bad idea, not be a bad idea here, guys, to write a quick little list of what's A and what's B in this expression right here. A is the cube root of this term right over here, so that's just going to be x. And then b is the cube root of this term right over here, and the cube root of 343 we said is 7. So that's going to be helpful then when we try to follow this factoring pattern that we wrote down here, and we're looking at, I forgot which one this was. This was a difference of cubes. So we're looking at this pattern right over here. So we begin with the binomial of a minus b. Well, our a value we said was x minus our b value was 7. So that's how this factoring begins. And now we start a trinomial right here. And we begin, let's go back to the pattern right here with an a squared. And then it's going to be plus ab and plus b squared. Okay, so a squared, a was x, and when we square that, we're just going to get x squared. The next term right now is going to be a plus. One good thing to remember here, guys, whether we're doing a sum or a difference of cubes, whatever sign you have right here comes right down into the first binomial. That same thing will happen on the next example. So that's one good thing to remember. A second one, there is only one minus sign in either of these two expressions. Here in the sum of cubes, it happens right there, but the other terms are all plus. And in a difference of cubes, it happens right here. The other ones are all pluses as well. So I know that this next term is going to be a plus. And then it's a times b, the product of this number times this number. X times 7 is just going to be a 7x. And then plus, we have a b squared at the end of all that. So if b was 7, we're going to square that to get 49 right here. And normally, I would tell you guys, you should think about this quadratic trinomial right here and see if maybe it factors even further, except I gave you guys a little hint here a while ago. That quadratic trinomial that you end up with from either a sum or a difference of cubes will never factor any further than it is, not if we're dealing with whole numbers right here. So you don't really have to worry about splitting that one up. So what that means, guys, is that we are pretty much done with this one here. Let me get that guy out of the way. Now, real quick, you could check your answer, as I'd always encourage you guys to do, by doing, not really FOIL in this case, but this one is a binomial times a trinomial, so let's try it. I'm going to distribute this x over here into the trinomial on the right. X times x squared is going to be an x cubed. X times plus 7x is a plus 7x squared, and the x times the 49 is a plus 49x. Now, I'll distribute the negative 7. So that's going to give me a negative 7x squared. Negative 7 times 7x is a minus 49x, and then negative 7 times 49 is minus 343. And something cool happens here when I go to combine like terms. Plus 7x, minus 7x, gone. Plus 49x minus 49x, gone, and we end up then with just an x cubed and a minus 343, which of course is exactly equal to the original expression that we started with. So check that one off. We got that one right as well. But again, just to be clear, the check isn't your final answer. This is the factored form of the original expression that was given to you in standard or expanded form, whatever you want to call that. So once you get the hang of the pattern, there really isn't that much work to do when it comes to factoring a difference of cubes. Now for example number 2, kind of the same setup right here, except here clearly we're dealing with a sum instead of a difference. But let's take a look at those two terms right there. 27x to the 12th. Is that a perfect cube? Well, if we go back to our list, 27 is a perfect cube, so that's good. But a lot of people want to look at this and say that x to the 12 is not. Their reasoning is because 12 was not in this list right here. But guys, the rules for exponents are a little bit different. A variable raised to a power will always be a perfect cube if this exponent is divisible by 3. And in this case, it is. I'll show you that in just a second. So yeah, this first term is a perfect cube, and 125 was in that list of perfect cubes as well, right? Right there. It's the cube of 5. So it didn't really look like it, maybe not at first, but this one is, let's go ahead and write this down, a sum of cubes. So we can factor it using the pattern before. Now, a is going to be the cube root of this term right here. And the cube root of 27 is 3. And for x to the 12th, you simply take that exponent, which is 12, and divide it by 3. So 3x to the 4th is your a term. That one might take a little bit of practice. B is the cube root of the second term, and the cube root of 125 is 5. Okay, so now that we know that, we can follow the factoring pattern we wrote down 2 slides ago for the sum of cubes. So now I'm looking at this one right here, guys, and it begins with the binomial a plus b. As I said before, whatever sign this is right here just comes straight down. So our a term was a 3x to the 4th. Because this was a plus, we put a plus right here, and our b term is 5. So that's the binomial we're going to begin this with. 3x to the 4th plus 5. Now we start a trinomial, and here we go. We take a, first of all, and we square it. That's the first term of this trinomial. So 3x to the 4th times itself. 3 times 3 is going to give us a 9. And x to the 4th, let me write this down, times itself. X to the 4th times x to the 4th. That's when you add exponents together, guys, when you're multiplying, and we get x to the 8th. So 9x to the 8th is our a squared term. Now, here's the tricky part right here. I told you guys that whether we're factoring a difference of cubes or a sum of cubes, we always are going to have one minus sign in the whole thing. Well, this one didn't happen at the beginning. That was a plus, so the minus comes right here. All right, let me make sure we've got that right. Yep, we're talking about this term right here in a sum of cubes, so this is where the minus occurs. And then this next term is just the product of a times b. 3x to the 4th times 5 is just going to give us a 15x to the 4th. This last term is always a plus, never a minus, whether we're talking about a sum or a difference of cubes. And up next is b squared. 5 times itself is going to be 25. And that, you guys, is the factored version of this original expression. That's how you factor a sum of cubes. And I could check that one in green, but I think that's probably pretty good for where we are right now, guys. Okay, the second part of this section of notes deals with using these factoring methods to solve equations, but I think I'm going to cut this video off and then do that as a second one. So we'll pick it up here in just a minute with solving equations by factoring.